The collection of all elements from A and B is nothing but A union B. Any element in the set X intersection Y will belongs to both set S as well as Y. The diagrammatic representation of the operations on set is given by the Venn diagram. The universal set is always represented by the rectangle and the other subsets of the universal set is represented by the circles. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study about the operations on sets. Previous session, we have learned the sets, the representation as well as the types of sets. In this session, we are going to study about the operations on sets. So the first operation is the union of sets. So what do you mean by union of set? Suppose A and B are any non-empty sets, then A union B is denoted in this form, that is A union B. So it is defined as the set of all those elements which are in A or B or in both. For example, let me take set A is equal to 2, 3, 5. Set B is equal to 1, 3, 5, 7, 9. Now A union B means all the elements which is present in both A or B. So here if I write the set, it is 1, 2, 3, 5, 7, 9. So when we consider any element in the set A union B, either it belongs to set A or it belongs to set B. So therefore the collection of all elements from A and B is nothing but A union B. Next, note here, A union A is equal to A. If you take the union of the same set, then it results with the same set. A union empty is equal to A. So when you take the union of an empty set with the set A, then it gives you the set A only. Empty union empty gives you the empty set. Now if A is a subset of B, then A union B is equal to B. Let's take an example. Let's set A denotes A comma B and let's set B denotes A, B, C. So clearly from this set, A is a subset of B because all the elements in A are in B. So therefore A is a subset of B. Now if we take the union of these elements, union of set A and set B, it should be the collection of all the elements in A and B. So this is A, B, C. So clearly A, B, C is nothing but B. So therefore A union B will be equal to B if A is a subset of B. Next is intersection of sets. So let A and B be any two non-empty sets, then their intersection is denoted by A intersection B and it is defined as the set of all common elements present in A and B. Let's take an example. Let X is equal to A, B, C, D. Let Y is equal to A, E, I, O, U. Now we write X intersection Y as the common elements in both the sets. So we can see A is the common element in both the sets. So therefore X intersection Y is A. So that means any element in the set X intersection Y will belongs to both set S as well as Y. Now let's look at the properties of intersection here. A intersection A is A. A intersection empty. For example, we have X here. If we take X intersection with empty, so empty means it does not contain any element here. So there is no element in common with these sets. So therefore obviously it is empty. And intersection of two empty sets is empty. Now again if A is a subset of B, then A intersection B is equal to A. So if we take A is equal to some AB and B is equal to ABC. So what is the common element in both? A intersection B, that is AB. And clearly we know that here A is a subset of B. So therefore this is the smallest set which is present in B. So therefore A intersection B is equal to A. Whereas A union B is equal to B if A is a subset of B. Next is difference between any two sets. So the difference between any two sets is nothing but the elements which is present only in the respective set. For example, let me take A is equal to 1, 2, 3, 4 and let me take B is equal to 2, 4, 6. So A minus B is nothing but elements only in A. That means it is not in B. So first, let us see the common elements here. 2, 4 is common in both. A minus B means the element which is only in A, not in B. So only in A is 1, 3. So therefore, A minus B is nothing but 1, 3. We can also define B minus A here. And when we say B minus A, it is the element only in B, not in A. So only in B means it is 6 because 2, 4 are in A. So when we are defining the difference of two sets, that means it is the element present only in the first set, not in the second set. Next, symmetric difference. So we have defined A minus B and B minus A here. So if we take the union of these two sets, that is nothing but the symmetric difference. So let A and B be any two sets, then the symmetric difference between A and B is defined as A minus B union B minus A, and it is denoted by A delta B. So if we take the union of these two sets, then A delta B will be equal to 1, 3, 6. So therefore, the union of A minus B and B minus A is called symmetric difference. Next, complement of a set with respect to the universal set. Now, assume that U is a set which contains an element A, E, I, O, U. So set of all ovals in English alphabets is an universal set. Now let me consider set A which contains A, E. Now clearly, A must be subset of U when we are defining the complement of a set. So this is possible only when A is a subset of U. Then A dash is a set which is defined as U minus A. That means A dash contains the elements which is not in A. So what are the elements which is not in A? I, O, U. So the complement of A is nothing but A dash, which is defined as U minus A. Next, we come across the algebra of sets. So algebra of set, the very first property is commutative law. So when you take the union of any two sets, so let us take A union B. So A union B is always equal to B union A. So it will be the same. So when you take the union of a set 1, 2 union 3, 4, then the resultant will be 1, 2, 3, 4. So let this be A and let this be B. So now let's take 3, 4 union 1, 2. Again it is 3, 4, 1, 2. So they are same. Only the order of the element is changed, but they are same. Similarly, we can define A intersection B is equal to B intersection C, which means the union and intersection of the two sets are commutative. In the same way, we can also define the associative property with respect to the union and intersection of a three sets. Let us consider A, B, C are three non-empty sets. Then A union B union C is same as A union B union C. So this is the first property, that is union of sets is associative. Similarly, we can define the intersection of set is also associative by taking examples here. So A intersection B intersection C is equal to A intersection B intersection C. Next property is the distributive law. Now A union B intersection C is equal to A union B intersection A union C. Similarly, A intersection B union C can be defined as A intersection B union A intersection C. So here the union is distributed over intersection and the intersection is distributed over union. This also satisfies the property of distributive. Next, De Morgan's law. So De Morgan's law is defined for the complements of a set. So assume U be the universal set and A is the subset of U. Then similarly B is the subset of U. Then we can define A dash as well as B dash. That is the complement of set A and complement of set B. De Morgan's first property says that A union B whole dash is equal to A dash intersection B dash. That is, the complement of A union B is nothing but the intersection of the complements of A and B. The second set, De Morgan's second property says A intersection B whole dash is equal to A dash union B dash. That is, the complement of A intersection B is equal to the union of A dash and B dash. So these are called as De Morgan's law. So all these properties can be verified by taking A, B, C of sets. Next, we come across a concept called Venn diagrams. So Venn diagrams are a diagrammatic representation of all the operations of sets. We can represent A union B, A intersection B, commutative, associative, distributive property also, De Morgan's laws also. So the diagrammatic representation of the operations on set is given by the Venn diagram, and it is designed by the mathematician Venn, and hence it is called as Venn diagrams. Now let us take an example of representing a Venn diagram. So universal set is always represented with the rectangle here. Here I have considered one set A here, and I have taken the example of universal set and a set A which is a subset of U. And we can clearly see the universal set contain all the elements from 1 to 10. So the rectangle always represents the universal set, and any subset under the universal set is represented by the circle. The set A contains the even numbers from 2 to 10. So the set A complement, which is nothing but outside the set, the region which is shaded in blue is your A dash. That is A complement. So clearly the universal set is always represented by the rectangle, and the other subsets of the universal set is represented by the circles. Let me take an example whenever two sets are defined as a subset. Venn diagram for subsets and supersets. So here clearly A is a subset of B. When A is a subset of B, B is called the superset and A is called the proper subset. And this is the universal set which contains B and A. That means A and B are the subsets of universal set. Also, A is a subset of B. So therefore, A is inside set B because A is a subset of B. A, B is inside the universal set. Now, other operations on Venn diagram is represented in this form. The very first clearly represent the complete set A, and here it represents the A dash, that is the complement of the set A. So we know this rectangle represents the universal set, and we have two sets A and B here. This region represents the intersection of both A and B. That is, the common elements present in both A and B is written in this form. Now here this shaded region denotes set A, and in the second section you can clearly see the set A is not shaded, it is out of the region, so which represents A dash. That is, A dash is the complement of A. Now the second thing here, it represents the disjoint set. The disjoint sets are nothing but their A intersection B will be equal to empty. That means there is no common elements between A and B. They are the subsets of universal set, but they are not intersected with each other. So here they are called as disjoint set. Now we have already studied here A subset of B we have studied here. If B is a subset of A, then B will be inside A and both will be in the universal set. So clearly B is a proper subset of A. Next thing is we have here overlapping set, which is nothing but the intersection. So intersection of two sets is represented with this. So this is the shaded region which represents the intersection of two sets. And the next one represents the union of the two sets. So we know that union of two sets means the collection of all the elements in A and B. So this is the region. So that means A and B, complete region is shaded here. So which represents A union B. Now some list of the formula which helps us in the practical problems of operations on set. If A and B are two finite sets, then number of elements in A union B, n always represents the cardinality of the set, which means the number of elements present in the set. So the number of elements in A union B is always equal to n of A plus n of B minus n of A intersection B. So this is the formula to calculate the cardinality of the sets. So by this, we can also conclude another statement, that is number of elements in A union B plus number of elements in A intersection B is same as number of elements in A plus number of elements in B. If you add the number of elements in A and B, it is same as number of elements in A union B and number of elements in A intersection B. And the second case here, note, if A intersection B is empty, that means if A, B are disjoint set. Disjoint means there is no common elements between them. Then obviously number of elements in intersection is 0. In such case, number of elements in A union B is just sum of the number of elements in both the sets. Now if we extend this concept to the three finite sets, then n of A union B union C is given by n of A plus n of B plus n of C plus n of A intersection B intersection C. That means the common elements in all the three sets minus n of A intersection B minus n of B intersection C minus n of A intersection C. Next we have, if A and A dash both are finite sets, then number of elements in A dash is always equal to number of elements in U minus number of elements in A. Now take this as an example here. So we have number of elements in U is equal to 10 because U contains all the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the elements, the entire rectangle will represent the set U. Now let me consider number of elements in A. So number of elements in A is 1, 2, 3, 4, 5. So obviously number of elements in A dash is equal to 10 minus 5, which is 5. 1, 2, 3, 4, 5. So these are the elements which is present in A dash. So thus we can say number of elements in A dash is number of elements in U minus number of elements in A, where U represents the universal set. Now we can also find the cardinality of A difference B as well as B difference A. If we want the elements only in A, then we need to remove the intersection part. If we want the elements only in B, then we need to remove the intersection part. That means if we remove the common elements, we'll get the elements only in A. Similarly, we'll get the elements only in B. So theoretically, it is represented using this formula. Now let's take few problems related to the cardinality of sets. The very first problem here, in a group of 65 people, 40 like cricket, 10 like hockey and cricket. Both how many like cricket only and not hockey, how many like hockey. So here they have clearly given in a group of 65 people. So 40 like to play cricket. So let me consider the number of people who like to play cricket is 40. 10 like hockey and cricket both. When we say both, it is intersection. That means number of people who like hockey as well as cricket. So it is 10. And they have also given the union of two sets, that is n of H union C. So there are 65 people. Now we need to find out how many like cricket only. That means number of people who like cricket but not hockey. That means n of C minus H. So then how many like hockey? That is number of people who likes hockey. Now using the formula of cardinality, we know that n of A union B is nothing but n of A plus n of B minus n of A intersection B. Similarly here, n of H union C can be represented as n of H plus n of C minus n of H intersection C. So this is equal to 65. Now here this is n of H, we don't know, n of C 40 minus 10 is equal to 65. So n of H is equal to 65 minus 30, so which is equal to 35. So therefore, clearly we have the number of people who likes hockey is 35. Now I need the number of people who like cricket only but not hockey. So how many people will like cricket here? 40. So how many people likes cricket here? 40. So n of c minus h is nothing but n of c minus n of h intersection c. So we need to remove the common people who likes both hockey and cricket. Then we will get only the people who likes cricket. So therefore it is 40 minus 10, which is equal to 30. We can also represent this with Venn diagram. So let this be hockey and let this be cricket. So the number of people who like both cricket and hockey is 10. Now if you consider this circle as hockey, we already have 10 people and the remaining people who likes hockey among 35 is 25. Now 25 plus 10 is 35. So the number of people who likes hockey is 35. And when it comes to cricket, there are 40 people. If this is the circle C, 10 plus 30 is a 40. So this circle represents number of people who likes cricket. This circle represents the number of people who likes hockey. Now 25, 10, 30, when you include, the total is 65, which represents the union of all people. Now if I shade this region apart from the common, this represents the people who like hockey but not cricket. And here, this represents the people who like cricket but not hockey. So we can also verify the results with the help of Venn diagram. Next question. In a class of 100 students, 35 play football, 45 play basketball, 35 play indoor games, 10 play football and basketball, 15 play basketball and indoor games, 5 play football, basketball and indoor games. If 15 do not play any games, then find how many play football and indoor games. Now, out of 100 students, 15 people do not play any games. So that means the number of students who are involved in games is only 85. So let U represents the universal set. Then number of people who likes to play football, basketball as well as indoor game. Let that be A union B union C. That is equal to 100 minus 15, which is equal to 85. Now they have given the numericals here. The number of people who likes football is 35. The number of people who likes basketball is 45. And the number of people who likes to play indoor games is 35. Similarly, they have given 10 play football and basketball. That is A intersection B, which is equal to 10. Next, they have given 15 play basketball and indoor games. That is N of B intersection C, 15. 5 play all 3 games. That is N of A intersection B intersection C. That is equal to 5. Now we have a data here. So we can solve this with the help of Venn diagram as well as with the formula method. Now first let us see the formula. So we have N of A union B union C is equal to N of A plus N of B plus N of C plus N of A intersection B intersection C minus N of A union B, N of B intersection C, N of A intersection C. Now we need to find out the number of people who play football and indoor game. That is, we need to find number of elements in A intersection C. So we have here A union B union C as 85, N of A as 35, N of B as 45, N of C as 35, and this is 5. And here N of A intersection B, 10, and here it is 15, N of A intersection C. So let's add this. 35 plus 5, 40, 80. 80 plus 40, 120. 120 minus 10, 110. 110 minus 15 is equal to 95. So 85 is equal to 95 minus n of A intersection C. So therefore, n of A intersection C is equal to 95 minus 85, which is equal to 10. So 10 people likes to play football as well as indoor game. We can also represent this with the help of Venn diagrams. Now let me consider the rectangle here. So we have set A who likes football, set B who likes basketball, and set C who likes to play indoor games. So A, B, C. Now 5 people likes to play all the 3 games. 10 people likes to play football and basketball. In that 5 is already written. So remaining 5 will write here. Next we have the number of people who play both basketball and indoor games. We have 15 students. This is the intersection part of B and C. So 5 is already written. So remaining 10. Next, let us consider the circle B. Circle B is the number of people who likes to play basketball, which is 45. Out of 45, 20 is already written. So the remaining 25 will be here. Next, we will move on to A intersection C. We have found what is A intersection C. A intersection C is 10. So this is the part which represent A intersection C. Among them, 5 is already written. So the remaining 5 will be written here. Now let's move on to section A. So A is 35. So out of 35, 15 is already written. So the remaining 20 will be written here. And let's C is also 35 here. So here we already have 20. So the remaining 15 will be written. And we have 15 students who do not play any other games, which is written outside this circle. So 15. Now if you add all this, you will get the value 100, which is the universal set. So this rectangle will represent you the universal set. The next question is, in a class of 150 students, each student is required to take at least one of the 2 subjects, namely biology or economics. If 75 students have taken biology and 25 have taken both biology and economics, how many have taken economics? Show that the result with the help of the Venn diagram. So let us write the data given here. So we have 150 students and each student should opt for biology or economic. So therefore, the number of students who choose biology or economics, that is equal to 150. And number of students who choose biology is 75. And number of students who choose biology as well as economics, and economics is 25. So we need to find out the number of people who choose economics. So with the formula, we can write here n of B union E is equal to n of B plus n of E minus n of B intersection E. So we have this as 150, which is equal to 75 plus n of E minus 25. So 150, 75 minus 25, again minus 50 will give you number of people in economics. So therefore, n of E is equal to 100. Now, if we draw the Venn diagram for this, okay. So we have, this is set U, universal set, set B, which represents the number of students who have taken biology, set E, which represents the number of students who have taken economics. 25 students have taken both biology and economics. 75 students have taken biology, out of which 25 is already written. So the remaining 50 is written here. So 50 plus 25, 75. Next, economics, we have already 25. So the remaining 75, which is represents 100, 75 plus 25, represents the number of people who have taken economics. So this is the Venn diagram. So in today's session, we have learnt about the operations on set and some of the practical problems related to the cardinality of a set. I'll meet you in the next session with a new concept. Until then, keep watching, keep learning, and keep exploring. Thank you.